I think.
Alrighty, let's start our next topic. It's still in special relativity, of course. I hope to get through this and then before the end of the hour, maybe have 5 or 10 minutes to go over questions on the homework as you have them, or check it off, or whatever. But today we're talking about linear momentum. Possibly the most important and hardest to find anything even close to breaking it, laws in the universe, is the conservation of momentum. This might be the most fundamental physical law. Well, let's talk about this for a moment. Let's say that you have an experiment in which you are accelerating a ball really, really fast. You know, half the speed of light, say. It's going to have a lot of momentum, right? So let's just draw this. Let's just say that the ball is here. It's got a velocity equal to about 0.5 c. It's got a mass. It doesn't really matter what the mass is, though. Because whenever you find momentum, you're going to say that momentum of this ball is equal to its mass times its velocity. Fair, right? And now you know we studied how if we have an interaction between that ball and something else, the momentum of that, it could be transferred, but it will be conserved. Same before and after, and everyone will agree on that. It's super important. Now let's put this on a spaceship. And let's say that we're here on Earth. It 0.75, or even 0.25. Let's say the velocity of the ship, since we haven't talked about adding the velocities. Let's say that the velocity of the ship is something high. If you're on Earth, how fast is that ball going? It won't be exactly 0.9. We'll learn how to add those. But yeah, it'll be quite a bit higher than the 0.5 c anyway. What happens to the momentum? It's higher, a lot higher. The same thing looked at from two different areas has different momentum. That is a big problem for the conservation of momentum. It means that the momentum is different, if that's true. Yes?
What is momentum?
Momentum it's what we did the last chapter. It's the product of an object's mass times its velocity. But if we can't agree on an object's velocity, since that's always relative, what do? Yes, ma'am?
How would the momentum be different?
What's its velocity to a person on Earth? Higher than 0.5. So that person would say its momentum is its mass times its velocity, and the velocity is higher.
Okay, so say the velocity of the ship is 0.6.
Okay. It can't be 1.1 c. We know that already.
So,
We're going to get there.
Okay.
I don't know if that's later this week, I don't remember,
Okay.
or early next week.
That can't happen.
No, that can't happen. You're absolutely right.
So, wouldn't this be the same thing if there were like a train on Earth?
Mm-hmm. Yep. Same thing for a train on Earth. Yes.
Would the momentum change though?
What's that?
Would the momentum change as well?
Yes.
Depends on who's measuring it, right?
Yeah.
It's an issue no matter how we're looking at it. Because we're talking about relative speeds now. And so we have to take this into account. So, because of this and because of other interactions it can have, what we find is that at these relativistic velocities, which is some reasonably high percentage of the speed of light, momentum is not conserved for all observers based on how we defined it earlier. The classical definition. So like the Newton. So we have two choices. Either we give up the law of conservation of momentum, which has appeared to work in every single situation, barring these hypothetical Tom ones, or we have to redefine what momentum is to make that agree with our law that we have observed. Now, granted, we don't know exactly what's We don't have experience with things going this fast. In certain high-energy physics labs, we do. But in our everyday lives, we don't. So we have to, and especially back when Einstein was formulating these new rules, no experience like that at all. So let's talk about what we need to do with that. Let's first talk about how we can define it. When we had our classical definition, we said that momentum is the product of mass times velocity. I took out the vector notation for simplicity here, which is an object's mass. And we'd find the velocity by taking the distance it's traveled, delta x, multiplied by the time it took, delta t. Confused by this? Oh, okay, good. Because that's the part that we did last chapter. But now, what's the problem with this, especially these two terms, if something like our spaceship is moving nearly the speed of light? What's delta x? What's the distance? What's the time? It's different. We've spent the last week seeing how those two things are different. So let's do a slightly different definition. What we're going to do here is replace those delta x and delta t with the proper measurement of each, because we might not be able to measure these directly, but we can figure them out. And this will say, in the proper frame of reference, the momentum still works. And it has to, because that's that fundamental law that we have. So now I believe I have another insightful derivation to pull out. Oh, it's a good one. It's a full page. It actually is partly already up here. But let's see how to handle this, especially with those delta x knots and the delta t knots. We're going to start with these two definitions up on the board and just see, based on what we've already learned about figuring out both of those, how does that translate and help us figure this out more? So first thing is first, we've got this delta t naught, which is the proper time, the measurement of time that would be made moving along at the higher speed, or wherever the experiment is going. And we know from one of our first, well, from the first major one that we developed, that we can rewrite that as the delta t, so the kind of the outside time times the square root of 1 minus b squared over c squared. And so if we put that in here for our relativistic definition, instead of the delta t naught, we get a mass times our delta x naught over the change in time times 1 minus v squared over c squared. Okay? Now, if we are on Earth measuring a ship that goes by, we would be able to measure its progress from point A to point B. We could do that because we're not moving relative to those. So we'd be measuring the proper distance there, which I'm going to call delta x naught. But because we are on Earth here, and we have our own watch, we are not measuring the proper time that the ship would measure. We are measuring the dilated time, the delta t. So the velocity that we measure for this ship would be, I guess it's a quotient, but it's the result of dividing these two together. This would be what tells us the velocity, what we can measure from our vantage point on Earth about how the ship is traveling. And we would call that its velocity. If the ship measured it, it would be reversed. They would measure the contracted length, delta x, but the proper time, still come up with the same answer. Because we're measuring the velocity, we agree with that. So this is velocity according to an outside viewer. Now, with that said, if I take this, delta x naught over delta t, that's what I have right up here. So my only other step here is I'm going to put this back in, this velocity that we could measure between us and the ship or whatever, back in, and it's a very almost recognizable form now. We've got the mass of the object times the velocity over this 1 minus v squared over c squared term that we've seen so often. And the only thing that I'm going to add to this is that this mass must be the mass that we'd measure if we were at rest relative to it. So we're going to add a naught in here. And what's that?
Isn't it the same formula with the v?
What do you mean with the v?
Because since v equals the change in x.
These two are the equivalent, yeah. Yeah. I'm just showing you how we get here because this delta x and the delta t are what we'd measure as the speed. But what this implies is that this is really similar to our original momentum, the p equals m times v, with the exception that instead of just the mass, now we have to define, it's the rest mass, what we would normally measure here on Earth that we're used to, divided by this. So this sort of implies that there is a relativistic mass. I'll make a better end there. That is equal to our rest mass divided by that really common radical again. Like so. So things, when things are going really fast, they measure time more slowly than still things. They get shorter, and what happens to their mass as they go faster? It gets bigger because this radical is always less than 1. And so it's the rest mass, what we measure here on Earth, or when we're with it, divided by something less than 1, it's always bigger. So the time for it gets shorter, its length gets shorter, and its mass gets bigger. This we have measured many, many times in those high-speed physics experiments when you're slamming a beam of electrons into something else. We can measure this very, very accurately now. And because those small particles we can actually make go about that fast. This is, by the way, we call this a relativistic mass. The mass is not a real thing as much as the length contraction is. It's really wound up in this momentum. The momentum is a real thing. But the mass is sort of an effective result of that. It doesn't, and what I mean by that is, although this mass is much, much bigger, it doesn't create more gravity around it. It would have, in a collision, it would have this much effective mass, but it doesn't make extra gravity like a greater mass would normally do.
Is it relativistic or relativistic? Relativistic.
I was talking while I was writing.
Oh, good. That's curious.
Two is Okay, so let's see what this means with an example. Let's take something small to begin with. Let's take, oh, that all went up at once. Oh well. A water molecule.
Yay.
What is the mass of a water molecule? Yes, ma'am.
Good question. So, does that mean momentum just changes from mass times velocity to mass times velocity divided by?
Right. The mass that you would measure if you were still, if you could put it on a scale yourself, divided by that radical.
Well, from chemistry, it's about 18 ATM.
It is not ATM, AMU.
So I
Right?
said the wrong word.
Yeah.
Oh.
So it is 18
Yeah, that's right.
AMU because one oxygen is 16, two hydrogens are each 1. How much is an AMU?
It's
Yeah.
I know what it is. I don't know how much it is.
I don't remember.
what's the
That's what I'm trying to find. So very often in science books, in the covers, you'll have things like that.
AMU equals.
I have the amount of kilograms per mole, so we could use that. It is also 0.0180 kilograms per mole.
Oh, I got the formula to
It's
gram.
right here. It's
Okay,
1 AMU equals 1.6605 times 10 to the negative 27 kilograms.
Yeah. It's really big. I have a gram to
okay. What's 18 times that?
Too big.
Too small, yeah. It'll be 10 to the negative 26 or so.
2.9889 to the negative 26.
9, we'll call it, just around times 10 to the negative 26 kilograms. So either way would be an okay way to convert it. Let's leave it in AMU for now, because that'll be way easier to multiply with, but then we could translate that to see, well, we won't even need to. So, the apparent mass, and here it isn't apparent because it's really based on the momentum rather than the mass. But let's find out the relativistic mass. So that m naught is what we would measure if it was still next to us. So this m naught is our 18 AMU. Let's put it in and find m, the relativistic mass. So we'd have 18 AMU over square root of 1 minus, remember our c's are going to drop out when I put them in there, so I'm just going to square this value.
I thought you already squared it. It's like, how do you?
Which is going to be a number very, very close to 1. Yeah, you can't really, these numbers a lot of times you can't really take in steps because there's going to be so much rounding on your calculator. It's best to put them all in at once. So take the 18 divided by that radical.
I still think that.
Why am I
got
getting 12,000?
Yeah, 1,272.
Because you didn't round it to the appropriate number of sig figs. 1
It
point.
should be around
You
1.
said we typed in what's on the board.
Well, it depends on what we define this. If we say it's 18.0, maybe, or 18.1, we're going to be pretty close. So I'm going to keep 3 sig figs. What units were AMU? That is 71 times more massive.
We just made a really heavy molecule.
Right. That is some heavy water.
So when you go faster, you get more mass.
When you go faster, you effectively get more mass. But really, it's a momentum thing. But we can kind of treat it like a mass, because when it hits something else, it's going to hit it with this effective mass and a speed nearly the speed of light.
So what is it to grams?
Just multiply this by 1,000, and you'd have grams 10 to the 23, negative 23. Heavy water, by the way, usually has 1 or maybe 2 extra neutrons, so it'd be 20 AMU. But now this is 1,270. Yes, ma'am.
So, that was just molecules, so what about a person?
Same process. It's just a lot harder. We'll discuss in a little while the energy needed to do this. So the energy needed to accelerate a person to this this speed would be enormous.
I got the number.
Okay?
3.7973 times 10 to the negative 23rd.
All right. But it's still 71 times the normal.
Yeah.
So. Okay, let's do it. Let's look at accelerating a person then. She's so big now, though. That doesn't look like her almost at all. Yeah?
Unless you have slowly.
You sure it wasn't just moving really, really fast?
Duh. Why do you think it takes so much energy?
Okay, so Ivy Rue at this point weighed 23 pounds. How fast would she have to pump her little legs in order to have the same apparent mass as me? 150 pounds. She's not a fast runner, by the way. She's a pretty good. She's becoming a pretty good dancer, but she is not a fast runner. Better than most her age. She knows what physics means.
That's good. You should show her a Physics Illustrated when she gets older.
I have. She likes them. Yep. And she's getting to the point where she can read a lot of it. Not quite
so
all.
that's how you grade them. You just have her read it.
We're getting there. She's in first grade right now, but maybe next year. Okay, so we got to define the proper value and the relativistic value. M naught and M. Yep, Skyler.
Would M not be 23 pounds?
Why?
Because it's a smaller value in her proper weight.
Her proper weight, yep. And by the way, we're using weight here, but since we're comparing apples to apples, weight to weight, we can get by with that because any correction factor will just be taken out. So technically speaking, this is a weight, not a mass, but since we're using the same.
And like it's M naught because she's moving relative to you, right?
What's that?
And it's M naught because like M naught is the weight of something
Right.
moving relative to you, right?
When we weighed her, we were at rest
Yeah.
relative to her. Yep. And what about her relativistic mass then? That would be the 150 because we want to figure out more about it. That's more my end of summer weight than my middle of winter weight, but still. Okay, and we want to find the V. So we've done this before. We've rearranged this before. We have M is equal to M naught over the square root of 1 minus V squared over C squared. I'm going to multiply by my radical, divide by the M.
Can you just do like the beta or whatever Greek symbol you
The
said?
gamma? Yeah, you can if you want. I think I'm a little confused because I have this written. The only thing is, based on what I wrote here, the gamma might actually be the 1 over the radical. Because I have this written as gamma times M naught times V. So I'm a little sketchy on if it's just the radical or if it's 1 over the radical. So I'm just going to write out the whole radical to
Can I
make.
just make gamma being the V
You
squared
may
over C
if you want to
squared?
do it that way. You may just don't screw it up. We're going to put it back in the radical right away anyway. But I'm going to multiply both sides by that
What?
and divide by my M at the same time. 2 algebra steps at once because I only have this much space.
So,
I multiplied by this to get it up on top, and then it'd be m times the radical, and then I divided by the m. I'm going to square it next. I'll subtract the 1 from both sides. Oh, and that's negative now. And I'll again multiply through by the negative c squared to get rid of this negative, but then only distribute the negative. So I'd have c squared times, this multiplied by negative 1 would be 1 minus, positive 1 minus m naught squared over m squared. And then I'll take the square root of both sides to get the final description of v. So you'd have v is equal to c times the square root. Now this is something that we're finding a lot, very similar form. Whenever we want to find the velocity, we're going to have c times something in a radical that compares the proper and the relativistic values. And I don't have room to put the numbers in, but we've got the numbers written right up above. So 1 minus 23 squared over 150 squared. Take the square root of that.
I want to know where people come up with these formulas.
Well, you've seen how they come up with these formulas. We've derived them.
I mean, the original one.
We've derived that too.
but we skipped
Right? Because remember, we started with that photon bouncing back and forth. We did derive all of these.
Oh.
So it's your fault, because you were helping. Yes, ma'am.
you did sort of skip a lot when you talked about them splitting it through a mirror and bouncing it back and forth. Like all
Yeah, but that was a measurement that showed that the speed of light didn't change. So that was just verifying that. What do we get?
0.988 C.
988 C. 0.99 C, depending on, probably only 0.99 because we've got 2 sig figs in both of those numbers. So 0.99 C.
Wow.
That's why it's
So she'd have to be moving pretty good.
Basically, speed of light.
More than
Pretty
you
darn
said.
close. Although we'll see with one of our next lectures how even going that last 0.1 is each incremental step that you get closer and closer takes more and more energy, so we won't be able to ever get up to the speed of light, even with little Ivy.
Wouldn't any part that the skin touches when she's moving that fast, like the skin would start to melt?
Oh, I don't know. It's
That's a theoretical.
yeah, it's a hypothetical Tom problem.
Yeah, let's use Tom, but
I like that a lot. Hypothetical. It's not related to you. It's hypothetical, Tom.
hypothetical, like Tom.
Okay, that's where we're going to put it up for today. But so, any questions before we put this up on this? No, but it looks like we've got some questions for on the length contraction and
Does hypothetical Tom play the guitar?
does what?
Does hypothetical Tom play the guitar?
I haven't asked him.
You should ask him.
My question is about your red bumper sticker.
Yes,
You'd have to be going the speed light to see a blue.
not quite.
No, it's
No,
not
Say it.
If this is, yeah, it's a Doppler effect. If this sticker is blue, you're driving too fast. You know how at a race you will hear the pitch of the car's engine change, whether it's going closer to you or farther away.
galaxies.
That's because the sound waves emitted, since they're being emitted from something getting closer to you, are kind of squished. Because let's say it emits a peak here, right here, and then it travels for a little bit and emits the peak here. Well, if it were still, they'd be a little farther apart, those spots. And the effect then brings those peaks closer together, which means higher pitch. When it's going away, just the opposite, so it stretches them. Light does the exact same thing. Now, we don't very often see a blue shift in nature because that would mean something is coming close to us. But we do use redshift to measure how fast other galaxies are moving away from us. And in general, galaxies are moving away from us and everything else, which is one of the big things. That's what first brought the conclusion of the Big Bang out, that everything seems to be moving away from everything else. We are going to collide with the Andromeda Galaxy soon, though.
How soon is soon?
5 billion years.
Oh, okay.
Yeah, but our standards will be lax.
Might still be alive.
The sun will still be around, and at that point, it should still look very much like our sun does now. It'll be getting to the end of its midlife. Earth will almost certainly be dead long since. It's weird to think about, but that's the unfortunate truth. Earth is unlikely to support life for that much longer, even assuming that we don't destroy it. Because my guess is that we would look more like Mars by that time. Because if Earth, the dynamo inside Earth, the moving rock and magma, if that stops, we no longer have a magnetic field that protects us from all of the energetic particles from the sun. And so those energetic particles will strip our atmosphere. Which is why the moon doesn't have an atmosphere, or very, very thin, and why Mars has a very, very thin atmosphere. Right, and all of the water vapor will go, and yeah.
I would not
Yep.
want to be alive for that.
Good news is we won't be. That should be a long, long time in the future yet.
And wouldn't the planet also be frozen, like freeze from the inside out,
It will.
like Mars is?
Is it frozen from the inside out?
Yeah.
I wouldn't expect so
The
because,
core is frozen.
well, that's
not
a.
exactly hot as compared to ours.
Okay, not as hot as ours, but hotter than the surface. Because why is it hot?
So it's compression.
Because of the compression due to gravity. That's still there. Maybe not hot enough to keep the core
Yeah,
molten.
it's not turning.
Right.
All of Mars' water was underground because it's so cold.
Yeah. Well, and everything that evaporated was blown away. Yes.
Is there more faster or more like
There is a 50% chance that we are in the middle. 50% of life's
We either
of Earth's
are or
life.
we aren't.
there's a 98% chance that we are in the 98th percent, middle 98%. So we're neither in the first 1% or the end 1%. So that's kind of comforting. I forget who came up with that, but it's a way of thinking. Basically, it goes along on the premise that we are not special. Right? And so we live in a time that is no more special than any other time. And so statistically speaking, there's a 50% certainty that we are in the middle 50% of Earth's life. Yes?
Somebody made a really realistic model of the Earth to figure out how much longer the magnetic field will last. I don't remember how long it was, but it's right now the magnetic field of the Earth is less than a fridge magnet. That's what I heard anyway.
Yeah. But I'm not sure that it was ever that much more.
Yeah.
So, yeah, it is. I mean, you bring a fridge magnet next to a compass and it deflects the compass. We'll do that in a couple chapters.
Yeah.
Not with a fridge magnet. They're uninteresting, but with other magnets. Yes, Matt.
So, what happens when the magnetic field, like the poles shift?
I don't know.
Anything could happen.
Well, just
They are moving slowly. From what I understand, it happens quite quickly, so that we aren't exposed to the radiation, really.
so it'll just be like, oh,
Yeah.
okay, this is happening now.
Yep. And it is moving. It's moved a lot in the last 50 years. Okay, but let's try and get through some of these questions. So, conceptual questions first. I've talked with this with a lot of people. A baseball player at home plates.
Which one are we talking about? Oh, no.
We're old, yes.
It's still on video too.
I know. A baseball player at home plate hits a pop fly straight up, the beginning event, that is caught by the catcher at home plate, the ending event. Which of the following observers records a proper time interval between the two events? So before we even look at the different options, how would the person have to be moving in order to be able to measure the proper time between those two events? Sorry? Not well. We can't say not at all because we don't know that any point in the universe is still. So what do we have to say instead? To the two events. The ball is still going up and down, but the two events occur at home plate. So even if we just say that they are within space, so anywhere in the field, if we are not moving relative to point A and point B, then we can measure the proper time. So, is a spectator sitting in the stands unmoving relative to those 2 points? Yes. So that spectator, provided he or she is paying attention, could measure that. How about a spectator sitting on the couch and watching the game on TV? Still, at rest compared because they're not moving in comparison. How about the third baseman running in to cover the play? Why? He's moving. His position is changing relative. So now it would be such a small amount that you'd never notice. And besides, the third baseman's going to have better things to do than measuring how long. Yes, Matt.
If the camera on the TV were moving, would that change it?
Then it would change it. Yep, because the camera itself couldn't make the measurement. But that would be like if it was on a track and literally moving, not just panning. That's okay.
If it's panning, it's fine?
That is fine. It's not really moving. It's just looking at something else. But if the camera is, or at least it's not moving appreciably, if it were on a track, like picture the rabbit in a dog race thing that's actually moving around the track, then it would be a problem.
All right. I thought that T-naught was when you were moving, and T and the regular TV.
T-naught is always when you're moving with the two events. It is tough to define, I know.
So then, is this problem with the third baseman be T-naught?
If he had his own watch, he would be the only one to be able to measure his own proper time. But he wouldn't be measuring the proper time of the two events, which both occurred at home plate. I know, I'm not saying it's easy.
Okay.
But remember, we're saying two things are moving relative to each other. Not that one is moving and one is still. So a lot of times the events will be just on the ship. So then that's going to be the proper time. Mm-hmm.
The rest of this stuff like this.
Uh-huh.
Not really.
Oh, yeah.
Would you say this is harder than physics 3?
Yeah. Yes. We got into a little bit of the quantum mechanics, but not much of the math. But now the next two chapters are not any harder. Yeah, math first. Maybe next year. Yes.
I still don't get why it's A and B and not.
Because the two events that occur are at places in the field. Okay? The third baseman is actually moving relative to the field. He's changing his position compared to the field.
Yeah, and the last time, every time Delta T-naught was someone moving between.
Yes, it does depend. So his time would be slightly smaller, slightly shorter than the person sitting in the stands. That would still be true because they're moving relative to each other. All it's saying is that for these two events, the hit and the catch, you can't be moving relative to them and measure the proper time. It's not saying which is shorter, which is longer. When we are talking about proper time of a person on a ship, what we have to say is, well, if the events we're looking at are the time that the ship takes off and the time that the ship lands, well, the ship's watch is the only one moving with the ship. Those two events happen kind of at the same place, according to the ship. The ship is here. Oh, the watch is still there on the ship. I'm not saying it's easy, but yeah. So the third baseman's time would be smaller, though, So if we wanted to calculate the times, we would still use that to represent him.
So how would you write it down in the test if that question came on? Would you say it's A and B?
You have to look and say who is measuring the time and not moving relative to those events. Generally speaking, though, you're on the test, you're going to be asked, you could be asked for something like that, or you could say, how much time would this person record given that somebody else recorded this? And we will still practice that, but that's where it gets a little hairy, I understand. Let's keep moving so we could maybe practice a couple of those. Number 3, the Earth spins on its axis once each day. To a person viewing the Earth from the inertial reference frame in space, which clock runs slower?
May I have your attention, please, for one quick announcement. Any of you who are in driver's ed after school, driver's ed is canceled. Again, driver's ed is canceled.
So there are so many interruptions this year.
Getting out to 2:40.
To a person viewing the Earth from an inertial reference frame in space, which clock runs slower? A clock at the North Pole or one at the equator? Why?
Well, I said the North Pole because it's doing the least amount of movement compared to the equator.
Okay.
Relativity.
Which clock runs slower? One going slowly or one going quickly? The quicker it goes, the slower it runs. So in that case, the clock at the equator would be actually faster for the exact opposite reason, because it is moving a lot more quickly. So the answer is the equator clock, because it's moving a lot more quickly than the North Pole clock compared to that person out in space. Right? The North Pole might not even be moving at all.
It might be panning.
You got a ways to practice yet. So think back to our twins. One of them left on the ship, the other stayed on Earth. Which one aged more? The one on Earth. Why? Moving slower compared to the rest of the universe. What's that? This is one thing that I can only describe it a couple different ways. A lot of it is you have to internalize it through the practice. Yeah.
If you are traveling, you always say that the watch has to be with, but
Yep.
they're further apart, but they're going at the same speed. Like, do they have to be right next to each other?
No, if they're really far apart but going the same direction at the same speed, they'll measure the same.
Good try.
Okay. We'll get into more of that. Let's do a little bit more. Suppose you are standing at a railroad crossing, watching a train go by. A, both you and a passenger in the train are looking at the clock on the train. Which of you measures the proper time interval based from that clock?
So we're measuring the same.
You're looking at the same clock that is on the train. Who can measure the proper time? The person on the train. Because they're traveling with the events there are the ticks of the clock. Who measures the proper length of the train car? The person moving with the measurement. Who is moving with that would be the person moving with the train again. Who measures the proper distance between the railroad ties under the track? Where are you? Outside. Because you are not moving relative to those tracks, so you get the proper distance between them. Yeah, all right. B was the person on the train. They'd be moving with that measurement of the length. Yes, ma'am.
So, does time get slower in movement in any direction?
Yep.
So like
It's a relative movement.
Moving in a circle, just out there.
We are aging slightly more slowly than someone who lives, say, Santa Claus on the North Pole, because we are moving more quickly. I don't know. Somebody keeps bringing me presents. No one.
Physics will prove that.